and we're going to continue by putting Rust on the GPU, I guess, because we want to go fast. And our speaker is going to be Mike Seddon. Please welcome Mike.
G'day, guys. The audio's all right? Cool. So I did talk a few months ago about WebAssembly. I think I had the same slide, but I'll quickly go. My history, I've done a lot of Scala for my sins with Apache Spark. And I sort of got so fed up with a lot of the things you had to do to make a JVM cooperate, and started looking at this project called Apache Data Fusion, which is a Spark replacement written in pure Rust. Really nice thing, getting to be quite mature if anyone's interested in that sort of stuff. My current job, we're doing machine learning for video. So we're doing real-time processing of video. We use Rust bindings to GStreamer. GStreamer is 20 years old, and they're still finding some pretty reasonably quality bugs. I bet you they wish they had Rust for that. But today I want to talk about GPUs because we're doing all this work on GPUs, but we kind of have to rely on a lot of closed source software, aka NVIDIA's CUDA. Part of my job is to look what's next, and I'm going to talk about some of that today. So we go to the fundamentals of computing with a single precision general matrix multiply. This is about the dumbest implementation you could do. It's not intended to be good, it's intended to be clear. But this is what is making GPT, and everything that you're doing on your phone is running machine learning all over the place at the moment. Series listening, it's doing matrix multiply a lot. There's a lot of this happening in the world, and so it kind of matters. In fact, the guy who does the double precision general matrix multiply, which is usually the benchmark stuff, won the Turing Award in 2011 for his work in keeping track of these supercomputers, getting better at basically doing the double precision version of this, because it's used everywhere. So you can see we've got some loops, terribly inefficient, but you can see how big these numbers get pretty quickly, like multiplying 1,000 by 1,000, and you're up at 1 million elements. And I think it's pretty easy for us to kind of forget what 1 million would actually be. Imagine if you had to take 1 million steps, or like $1 million. These numbers are actually pretty big. But then you want to apply this algorithm to it, and you're up at 2 billion. And we want it to happen many, many times a second, and we want it to happen all the time and be reliable. So I ran this on a little NVIDIA box at work, which is a Jetson series, so it's pretty small. It's got a 12-core ARM processor and a surprisingly good GPU, and got 0.7 gigaflops. I looked just before because I was trying to get some numbers. The Apollo 11 apparently had 15,000 flops. So, and I'm talking 7.7 gigaflops. So a gigaflops is 1 billion, yeah? So this is a consumer box, although apparently they're on the space station. But rubbish. So because we're interested in matrix multiply and we are Rustaceans, there is a library called FAIR, or I don't know how you pronounce it. This is a pure Rust matrix multiply. It's quite new, super fast, competitive with MKL, the Intel one, competitive with kind of everything. Really, really solid code. It's going to be awesome. And you can see immediately I install their library, turn on intrinsics, which are neon instructions and all that sort of stuff, and we get 38 times faster, as you would hope, because that first algorithm was completely rubbish. And then I turn on multi-threading and I get another 6 times performance on top of that. And you're getting to these numbers which, compared to the Apollo 11, this would have been, I don't know, if you took this back in time, I don't know what they would think you came from. So this is a really good library, and you don't need, the guy at work asked why we had a Fortran compiler, because MKL is still compiling Fortran, and OpenBlast does something else, but whatever. We don't really want that if we can do it with Rust, and this is the answer. So we're at 154 gigaflops, but gigaflops are kind of like this silly number that, you know, it's kind of hard to conceptualize. So I went and Googled and I looked at what GPT is doing. I don't know if this is right, but let's assume it is. These are Facebook's competitor to ChatGPT. They reckon ChatGPT has around 800 something billion parameters. So every time they do a forward pass on those neural nets, there's 800 billion parameters being involved. Facebook's released the 70 billion one that gets quite good results. If we multiply it by 2, we're sitting at about 140 gigaflops per token. A token is somewhere analogous to a word or maybe part of a word. So you've seen, I think you pay by tokens for GPT. And then you go online and you see these guys that run these things and they say, if you're not doing 20 a second, then it's too slow and it's shit. So we're looking at something like 2.8 teraflops. So we've gone up by another 1,000. And you need to do this continuously. And we'll get to why this is actually a lot harder than it sounds. So we at work, and just because it's interesting, we're trying to get this problem to be better. But GPU programming is really, you're behind this wall of drivers. And it is a big moat that we're sort of facing at the moment. Obviously, CUDA is the king, by a fair margin. But in the Rust community, we've got something that's emerging with the WebGPU standard, similar to WebAssembly. Sort of ignore the web part of it, because we can run these things not on a web platform. So Chrome will have it, but Rust has the implementation that is powering Firefox WebGPU implementation, called WGPU. So that little box that I've been benchmarking has, theoretically, according to NVIDIA, 4 teraflops of processing power. You cannot get theoretical performance because that's not how the world works. It's like, on your speedo on your car and it goes up to like 240 or something on my Corolla. It's a good idea. It's not going to happen. But I think if we're going to see what's possible, we go to the source and we find the NVIDIA guys and we say, what can NVIDIA get out of their graphics cards? Because they know all the tricks. And at this same size of 1,000 by 1,000 matrix, they're doing about 3.2 teraflops, which is about 80% throughput. Compared to our CPU, one before, even with multi-threading, was 21 times faster. This is a baby card, though, compared to what's out there. I looked just before. A 4090 has about 80 teraflops, so 20 times faster again. Then you get into the serious cards, the enterprisey cards, at about, they actually have very bad floating point 32 performance because they have specific instructions for floating point 16, so half precision. And they're hitting maybe 150 teraflops. And the new ones are coming out, I think, maybe over 200. So this thing is happening, and it's happening a lot. So this post, I ran this benchmark on that little box. There's a repo at the bottom. This guy has an excellent blog. If you're interested in any of this stuff, there's that link that we can send to you. He goes through the process of trying to match NVIDIA. And it took him like 9 months. And he goes through from the most basic one that you can see at the bottom, the naive one, all the way through as he experiments with these different things. Those blogs that come out occasionally and you're like, fuck, this is top quality. This is it, if you're interested in this problem. Anyway, so let's say we can get 80% or 3.2 teraflops out of this box, if we're good. In the Rust community, there are bindings to CUDA. This one is probably the best that I've seen, and I've looked through a fair few of them. It's written by a guy who's writing a machine learning library. You can see it's very high level. You sort of say, I just want a device. I'm going to load this PTX, which we'll have a look on the next slide. That's the actual kernel that you're going to run. Go and get it and launch it and pass some stuff, bit of unsafe. That's how you're going to do it. Wait for it to finish. Important thing. And this would be an example kernel. So when programming a GPU, I guess you have to think completely different to CPU programming, that you're not in charge. Well, you are, but you're not kind of... Your coding is if you're writing single-threaded code, and then the CUDA driver will take care of distributing that and running it massively parallel. And if you think about what Rust says, we have single principles of ownership. It's sort of like Rust programming and GPU programming are very different mindsets, neither of which I guess are right or wrong, but this is a way, and you can see that you're just defining that operation, and these block IDs are kind of indexes into a shared mutable buffer that can be updated by many, many threads at once, and that's how you're getting your performance. So I think it's pretty interesting, even if you've just read that other blog and you'd be like, fuck, this is really complicated stuff. Yep. Yes, please. Yep. That's all right. Yep.
So this looks like C code, and it may well be C code. But I'm trying to understand, how does this get to the GPU? Because I presume this function isn't being called over and over again. That's not GPU.
It is.
It is.
Yes. So this is the function that would be compiled once. So they're using this thing called PTX. Is this dialect, I guess they're doing. NVIDIA's actually forked, what is it called, LLVM, back at some stage in the past, and I think they're maintaining a parallel copy. But really, like, this is, writing simple code like this is what has made NVIDIA worth whatever it is today.
But this is compiled not to x86.
No, it's compiled to GPU.
GPU language.
Yeah.
Okay. So you could, in theory, have another language that compiles the GPU language.
And we'll get to that.
Oh, sorry.
So, that's good. We're segueing into the WGPU. So yeah, WGPU is WebGPU, but it is a Rust crate. It's the implementation that is being used for Firefox. I'm not sure if I like it yet, but what it's doing is it's abstracting away a few of these different implementations. So if you're running your Mac, you've got Metal. Vulkan is probably the leading contender to be a real threat to CUDA. Then you've got Windows stuff that I don't care about. And they use a different shader language. So when we talked about this thing, they're talking about compute shaders. In this case, we're using WGSL, which is probably, like, if you're coming from a Rust point of view, it's a lot more rusty.
So, if I'm like a noob, I'm mostly noob, so what is a shader?
Okay. So remember that graphics cards were for drawing triangles originally, and a shader was basically a program that ran on your GPU. And now, unfortunately, because of that history, we've inherited this word shader when it comes to compute as well. So I'm not shading anything. There's no pixels being drawn, but I'm using the same, like these GPU capabilities to run software. That's what a compute shader is. I think, yeah, it was, but I think, he's saying that the shader was the single, like the most atomic unit of compute originally. But yeah, basically our legacy is that we've kept this language into something that's got nothing to do with pixel drawing. Like, it's just one of these historic artifacts. It's getting tricky. Okay, go.
Let's say I have a C program that
Yep.
doesn't have any headers, so let's forget about I/O and all that. Just a
Yep.
C program. Can I compile any C program to the GPU target, or are there some
No.
C? No. So we only compile a subset of
So
C.
it looks like C, it's not C.
Okay.
NVIDIA C, let's call it.
So we can't compile Rust to GPU.
It's getting tricky.
So, can I run Linux in my GPU?
I'm sure someone has made it work somehow,
Yeah.
but don't. I've lost my train of thought. There is work being done by a gaming studio. I think they call it Rust. Yeah, Embark, Rust GPU. They're endeavoring, I don't reckon they'll make it, to compile Rust code to GPU code. But like you can't really use a GPU without going through the drivers that are going to be DRM'd and provided by the vendor. They're choosing what they expose to you, and we'll talk about that a bit at the end.
So you mentioned Mbak, who is like a big supporter of Rust community, and they actually have lots of open source things, and many companies actually could use them as like a template how to do open source. They've been focusing a lot on the Spear 5, or is this the Spear 5 what you've been talking that they've been working on? What kind of Rust stuff they've been working? So where they could find this stuff?
Okay, that was about 5 questions. Okay, so alongside this WGPU project, there's a project called Naga, N-A-G-A, and it transpiles different dialects of shader compute programs here, like this one. You could transpile this from, this one's WGSL, it can go to GLSL, which was the OpenGL old style. It can also go to SPIR-V or whatever, I don't know, SPIR-V, however you say that. From my understanding and reading of this, Apple heavily influenced a lot of the decisions that went into Vulkan. I think a lot of the stuff that's in WGSL seems to have followed, sort of that lineage. But it's also clearly come from some guys in the Rust world because it's very rusty in how it works. You can see, like, it could almost be Rust. This one's got some templating going on as well, but yeah, and you get some of the error handling that you might expect from Rust now. I think traditionally it's been very hard to write shaders because you don't get a lot of feedback from it, except shit went wrong. That's sort of, right? And anything we can do to make that better. So yeah, this is a WGSL example. It is parameterized, but you can see it's kind of the same thing, but compared to the CUDA level, you're down a level. Like you can see that I'm talking about bindings. And the whole time I've not talked about how you get data into the GPU before you even run these kernels, because it's a whole nother thing you have to do. Speaking of which, so this is the WGPU crate. If you go near it, be prepared because it is quite a verbose thing, because it is a very powerful thing. I think there will be abstractions written that are higher, but at the moment, it's not time to do that because this is still a moving target, and I think we should get this right before we worry about abstracting it away. So you can see I need to get a device, and in this case, like if I run on my Mac, I have a metal device. A metal backend first. That could be Vulkan, and they've got a Vulkan to metal transpiler, and I think that's also some of this lineage of Apple sort of dominating how Vulkan progresses. If you're on your Linux box, it'll probably be Vulkan. So Vulkan is kind of the unifying thing that I've got big hopes for. We'll hope. Once I've got my backend, then I ask the backend, what devices do you have available to me? So on my Intel Mac, I've got an AMD card and I've got an Intel card, like integrated GPU. And so each of those comes and you can kind of choose which one you want to use. But it's up to the vendor to do that mapping of, You know, like I'm talking metal. Metal now needs to implement a whole lot of instructions, and they're going to choose what they expose because they don't really have to expose anything they don't want to. So you can see quite low level, and I get my GPU. And I also got a queue so I can talk to it, and I'm probably running out of time. Here I've got an unsafe bit where I'm compiling a WGSL blob, which was that blob that we showed before. This code I wouldn't use. This is just benchmarking code. Again, taken from this guy at the bottom. He's written a WebGPU implementation of Whisper, which is a voice-to-text transpiler that's been released by OpenAI for free. He's done a WebGPU one. Fortunately, he put his matrix maths up, but his other repo is private, so I haven't been able to see in. But he's been testing these kernels to see what can get the best. And you have to go to everything. So you define an encoder, and you're building up a pipeline that you then go to the GPU, go and run. And this is all just to get this kernel started, and we haven't even looked at how you get the data into the kernel, which itself is quite a bit of work. But go and have a look at the repo. So he's gone and collected all of these kernels from everywhere he can get them and converted them into that WGSL. This one is the best one that he's found so far. This one came from TensorFlow.js, that someone, I don't know who wrote that. And they're sitting at about 2 teraflops, which compared to 3.2 teraflops with CUDA is looking kind of shit. Maybe. So you think what's happening here, this is going through Rust, talking to Vulkan eventually, and then Vulkan will map those calls. In this case, NVIDIA will map them, and they have to implement them. I don't think it's really in NVIDIA's incentive structure at the moment to make this process good, because then I've got a kernel that I could go and run on my Mac and on my NVIDIA box. And I think that's why we're seeing this sort of degradation, like 60% is really crap. It also could be, and I've been thinking about this after, that this is an Orin Jetson embedded machine. Are they really putting much effort into that box for this use case? I don't think anyone else is going to try to run Vulkan on it. Maybe they do. Probably not. So yeah, kind of disappointing. And it sort of made me think, is this going to be worth doing anything at the moment? But I mean, that's part of our job as engineers. We should be benchmarking and stuff and deciding when do we sort of move forward. But this is some of the... So there's a guy, GeoHot, that hacked the PlayStation, I think he did, years ago, and he's got a self-driving car thing, and he's writing a library called TinyGrad. I like him because he stirs a lot of shit, and he's stirring a lot of shit with AMD for their kernel drivers not working in Linux. And we need a competitor, and that competitor is probably AMD at the moment. But they found this kernel somehow using these intrinsics that are not published by Apple. And this is on an Apple M1 or whatever they're called, getting an amazingly high throughput level. So you can see that as more functionality comes into the Vulkan spec, maybe that 60% will become much, much closer to the CUDA, and the world will be a better place. So yeah, I think I'm hopeful. I think Vulkan is going to be a good thing. I think WebGPU, maybe. We'll see. Cool. Yep.
So my first question would be, you briefly touched on error handling. Yeah. The last time I did any compute on GPUs was like OpenCL 10 years ago at uni. Yeah. And error handling was not existent. Like you compile the kernel, you load it on, and then you either do or don't get a result, or you get one that is just wrong. What's the state now?
Better. You feel the Rust sort of ecosystem coming with you when you start to try these kernels. They're linted, they're error messaged. You get that nice, like, here's the problem, that error message that we love from Rust. Not that I have problems, but you know. Yeah, so I think it's actually pretty good. And in terms of dealing with the errors, so you've got the kernel errors, but then you've got the Rust side, which WGPU, you know, is a proper crate that will throw, that you can deal with errors the proper way.
And runtime errors
Yes.
as well?
Yeah, you should be able to. Yeah. But I mean, if your kernel's broken,
Runtime errors.
you bug it. Oh, runtime errors, yeah, because the WGPU crate will return results. And so you could deal with them. The thing is, like, I think when you're doing that sort of programming, you tend to not get runtime errors. It sort of, it starts and it works, or it doesn't work. You know what I mean? Because you're doing, it's not like you're doing a lot of wide operations. You're doing the same operations many, many times is probably the difference. Maybe that's wrong.
I was very interested in like the side incentive discussion about what incentives NVIDIA has, because my extremely naive understanding would be they would want to sell their hardware and make it good. So can you explain the background there?
Like, I've got full respect for NVIDIA. Like, their boxes are exceptionally good. But the problem we've got is that CUDA is closed source. When you download like the CUDA Docker images, which we do because like trying to get CUDA set up properly is a fucking disaster. So we download them and they might be 4 gigabytes, 5 gigabytes, because they've got heavily optimized kernels built for all sorts of different GPUs and different architectures, and they'll switch them out, but they're already compiled with there. And you don't get to say like, I just want, you know, this little set for my GPU, because they want everything to work everywhere. I think the reason NVIDIA is dominant is they were clever enough to make CUDA work on every card. And so, like, I have my Mac with an AMD card with the GPU that's basically useless for me. Like, I can't do any compute on it until just recently, because the software that AMD uses, called ROC-M, they didn't support on anything except their enterprise cards. And so there's no fucking way I'm going to go to work and ask for a $25,000 graphics card to maybe work when I can go to CUDA, run it on my gaming computer, then take exactly the same code and run it on, you know, a supercomputer. Like, they're killing it because of that. Yep.
As someone who's sort of been interested for a little bit and doing sort of these sort of calculations, GPU stuff, but has never done that before, do you have any sort of websites or ways to learn that you'd recommend, basically, for newbies to GPU stuff?
I think because WebGPU is quite new, I mean, they have, you know, their book and stuff like that, the Rust book. It feels, I don't know how to learn this well, to be honest. I've been doing a lot of reading and a lot of playing. I guess it's a good time because at least things are open source largely in this space. I reckon in the next few months we'll start to see some really interesting stuff come out because, yeah. Oh, and on your crashing question, somehow if I run certain code on my Mac, it will crash the Mac. So, like, boom. Yeah. So I guess there's sharp edges still. Yeah, just seriously, just breaks. So I don't know. I think it's going to be really interesting. And if you're doing real-time web, audio even, here you've got this supercomputer sitting next to your CPU you could use. I don't know. I think it's going to be really interesting. Sorry?
Audio processing is genuinely highly.
Yeah.
Oh, okay. Yeah. It was like audio processing from the talk before. Yeah, I was just going to say audio processing is generally very, very linear, so it probably wouldn't work so well on GPUs. From memory, there is a company that's trying to do it, and they've got some cool stuff working. It's just there's not really any meaningful advantage to it.
Yeah, I think maybe fast Fourier transforms and stuff like that are a lot quicker. They've been heavily optimized. There's a CUDA library, and actually there's a guy that wrote Vulkan fast Fourier transform library. I think he's exceeding NVIDIA. So there's definitely use cases there. Cool.
Yeah.
Cool. Thank you, Mike.